Kia ora and welcome to this video on energy. Today we're going to go over what energy is and be able to classify it as three main types: radiant, kinetic and potential. Learn lots about different types, and the follow-on of this video will be a light and sound introduction. So without further ado, let's begin. So I guess this is our first look at the world of physics, or in our curriculum, the physical world. And this includes some fields such as particle physics, which looks at the smallest things in our universe, atoms and subatomic particles. It seeks to answer questions like the origins of the universe. It also goes right up to astrophysics, which explores the universe such as stars, galaxies, black holes, quasars, pulsars and supernovas. And applies principles such as relativity and quantum mechanics to objects in space, so sort of a high energy physics, and even nuclear physics, which uncovers the potential hidden within the atomic nucleus, specifically unlocking new forms of energy. Nuclear weapons, nuclear power, medicine, engineering, and history, such as radioactive dating techniques, are all covered under that field of physics. So all of those sound some pretty impressive career options, but they're also all rooted in the foundation knowledge that you'll receive today. So, what is energy? Well, energy is defined as the ability to produce, change, or do work. And that work can be divided into several main tasks that we'll easily recognize, and I will go through in this video. So energy does things for us, basically. It can move a car along a road, boat on the water, it bakes a cake in the oven for us, and it keeps ice frozen in our freezer. It plays our favourite songs and lights our homes at night so we can read good books or watch videos like the one you're watching now. Energy helps our bodies grow and our minds think. Energy is changing, doing, moving, working. So let's unpack it even further. As I said before, it helps us realize some of these things. So energy helps us create light, heat, motion, sound. It allows our bodies to grow, and it allows our technology to function. How does it do this though? Well, we have two main forms of energy, and those are potential and kinetic. And we're going to unpack those today. So, potential energy is energy that is stored, and the energy of position, or gravitational energy. There are several forms, and examples of these forms of potential energy can be given in these four clues. So photosynthesis, you might have heard looking in doing some plant biology. A spring or rubber band you've all played with before, I'm sure. You've heard of an atom, and you've heard of a rock, and these all have potential energy. There are a number of types. So, the first type of potential energy is chemical energy. This is the energy stored in the bonds of atoms that bind together to form compounds and molecules. When these bonds break, they release energy. However, until they break, it is potential energy. During photosynthesis, sunlight gives plants energy, and they can build these complex chemical compounds that store this, called starch. And when these compounds are later broken down, the stored chemical energy is released as heat, light, motion, and sound. But before that, it is potential energy. Here are a few examples. Moving on to another type, we've got stored mechanical energy. And this is the energy stored in objects by the application of a force. Okay, and we've got things, this is also known as elastic potential energy. So things like springs when they're compressed and rubber bands when they're pulled tight are all parts of stored mechanical energy. Nuclear energy. Again, this is similar to chemical energy, but now we're focusing on the atom itself, and particularly the nucleus. And you've all heard of the famous New Zealander Rutherford, who split the atom. This is the energy released when you do that. You split an atom apart, and the immense energy within that atom is released. The sun combines nuclei in two hydrogen atoms into helium atoms in the sun in a process called fusion. When this happens, also a massive amount of nuclear energy is released. But until then, it is potential, it is stored energy. Here we have gravitational energy, and this is where the rock comes in. So, the energy of a position or place. So, if there is a gravitational field involved, like us on Earth, then you will have gravitational potential energy. A rock resting on a hilltop contains gravitational potential energy, and when you take away the support force that is holding it there, it will move. Okay, if we had a book on a desk and you deleted the desk if you could, the book would fall. But while it is on the desk, it has stored gravitational potential energy. So now we know about this potential energy. What does it convert into? And you might have got from where I was going with some of those examples before that energy can change. And it goes between the two types all the time. And this next type is known as kinetic energy. Kinetic energy is motion, the motion of waves, electrons, atoms, molecules, substances, and objects. Okay? So here's a quick task you can do. Pause the video, and can you list as many types of kinetic energy as you can, looking at these pictures as clues. So I'm sure you've all heard of these types of kinetic energy. Here are some clues. So pause the video now. Okay, did you come up with one for each of these pictures? Let's see if you got them all. All right, so the first type is electrical energy. Okay, and you saw this in the sort of spark between the two plugs that I had on the pictures. And this electrical energy is the movement of electrons. Applying a force can make some of the electrons move in a substance such as copper wire. Electrons moving through a wire is called electricity. Lightning is another example of electrical energy. Everything is made of these tiny particles called atoms. Atoms are made of even smaller particles called electrons, protons, and neutrons. And it's the movement of these electrons between atoms, because they can share them, that causes electricity. The next one is thermal energy. This is the internal energy in a substance, the vibration and movement of atoms and molecules within a substance, and the faster these molecules and atoms vibrate and move within a substance, the more energy they possess and the hotter they become. And this can radiate, conduct through vacuums and through objects. So we'll cover that a bit more in the next video on heat. The next one we have is motion energy. Motion energy is the movement of objects. The movement of objects and substances from one place to another. And we've all heard of this guy called Newton. He came up with the laws of motion. Objects and substances move when a force is applied. Wind is an example of motion energy, moving particles of the air or the atmosphere. We have sound energy. Sound energy is this movement of energy through substances using a longitudinal wave. Now, when we look at light, we'll look at the difference between light, energy, and sound. So we'll cover that in a bit more detail then. But it all has to do with this thing called resonance. And finally, we have radiant energy, or also known as light energy. Radiant energy is electromagnetic energy that travels in transverse waves. Radiant energy includes visible light that we can see. The reason you're able to watch me right now on this video is due to radiant energy coming off your screen. Light is one of the types of radiant energy, and we also cover things like X-rays, gamma rays, and radio waves with our radiant energy. We'll cover that more when we do light as a specific video subject. What's amazing, and plants are these amazing things, is they can convert this radiant energy and store it, so from a kinetic form of energy, into that chemical potential energy known as starch. It's quite amazing. We'll look at those energy transfers now. because this is the most important slide in the whole video, and that is you need to know this law, okay? This is the law of energy conservation, and that is that energy cannot be destroyed or created, only changed from one into another or transferred from one object to another. So what does that mean? Well, I've got this little graphic to show you. So if we think about a cannon shooting something, right when the cannon is not shooting anything, we have the gunpowder and we have the shell. The gunpowder is stored chemical energy. That chemical energy, when we ignite the gunpowder, changes into a lot of other things. Okay, mainly kinetic energy in the form of heat, sound, and motion of the shell moving through the air. As that shell gets really, really high, there'll be a point when it has gravitational potential energy, because all the motion has been connected into the shell. If you were firing it straight up, there would actually be a point where that shell would stop before it falls back to Earth. That's because all of its kinetic energy has been converted into gravitational potential energy, and then it starts again converting back to kinetic. And then when we have the shell exploding, maybe it is has a warhead on it that is a nuclear warhead. So we've got the nuclear energy in there that is then converted into massive amounts of heat, massive amounts of kinetic energy, and massive amounts of sound. So you can see in this small little example, energy doesn't just disappear. We don't just create it. It was always there in the first place. It is just converted many times through a process of action. So, how do we display this conversion of energy from one form to another? Well, here's some examples. Pause the video when I get to the bottom of this list and have a think about which ones you could write a small equation for. We'll do burning match first before you can pause the video so you know what I mean. So the head of a match is a chemical, and that chemical energy is stored and ready to be converted into other things. And we know the two main forms are heat and light, and it even makes a sound sort of when it crackles when you ignite it. So chemical energy to heat and light. Pause the video now and write down what you think the conversions are between the rest of these examples. How do we do? Let's have a look. So when you're carrying around a torch, you've got the batteries. The batteries are chemical potential energy stored in them, and they will release light. And if you hold a torch for a long period of time, you'll start to feel it heating up. Modern day LED bulbs, much better at not doing this, but older bulbs will heat up due to the process of creating light, forcing the electricity through a very narrow filament. You could even add that there goes chemical to electrical, electrical to heat and light. So you can add that in there. A microphone obviously projects sound from your voice into electrical and stores it on your computer, and then you can play it again, so it would convert it back to sound. Okay. You've got your radio, so obviously if it's plugged into the wall, it's electrical and converts it to sound and heat. Heat is often a form of energy that is released regularly with most conversions. Okay. Often referred to as sort of a bit of a wasted energy and isn't utilised very much in whatever it's doing. For example, we don't use a torch to heat us up. We use it for the light, so the heat is sort of wasted. Our television, again, plug it into the wall, electrical to sound, light, and most TVs get pretty warm if you leave them on for quite a while. Our catapult, if you've been in STEM with me in junior school, you'll know the best catapults, we use a lot of elastic potential energy, and when that's released, you get a lot of kinetic energy. Now, what you might not see or feel at the time is when an object hits another object, you get this thing called friction, which is a force that causes heat. Okay, so anytime two objects connect, you'll get friction. The mobile phone that keeps distracting you during class, yep, that has obviously a very powerful battery in it these days, and that is converted into the electricity to power sound, light, and the phones can get quite hot. And finally, cars. The main energy source or potential energy source in a car is from petrol, which is a chemical. When we ignite that petrol, we break the bonds, change the molecules into things like carbon monoxide, oxygen, and things like that. So that is converted into the ability to move, kinetic energy, but also beep your horn, bit of electricity in there as well we could put. And, you know, after a big long drive, the bonnet of your car is pretty hot from the engine. So here's another example of a energy equation that we could do. So the energy input, okay, usually stored energy, just gave the game away there, is the chemical energy in the fuel. The process of our engine breaking it down, okay, through combustion. These are combustion engines. And the energy output. I'm going to have to add a slide soon for electrical cars. So instead of this chemical energy being from the fuel, it's from the big lithium batteries that they're creating now. And the car engine will be these battery centers, and they will create the exact same things, but the chemical stored energy is from a battery rather than the breaking down of fuel. Try and do this one. Oh, didn't get my animations quite right there, but so obviously we've got a light bulb plugged in above me right now, and that needs electrical energy to convert into light. Depending on the type of bulb, you might get a bit of heat in there as well. Now, I just wanted to briefly cover power stations. So power stations here, you can see this one's a nuclear power station. You have a number of conversions and transfers of energy types. So obviously in a nuclear reactor, the potential energy here is stored in the reactor in atoms such as uranium, and that is broken apart during a critical nuclear reaction, and that creates an insane amount of heat. That heat heats up what we water, which makes it vaporize into water vapor, steam, and that drives down these pipes, high pressured, to move a turbine. Now, so that converts it into motion and kinetic energy. That then drives a magnet, and that magnet starts to move those particles, subatomic particles known as electrons, and they start to flow. They flow in massive numbers, so we need to make sure we transform that electrical energy into the right amount so we don't blow all of our appliances, and that's sent out into our cities and towns and houses. Very similar to a nuclear reactor is the hydro dam. Okay, we have the water this time creating the motion rather than steam. Okay, and that drives this turbine here. Again, in here is a giant magnet that starts to move electrons down our wire, and that wire then goes on to move our powerhouses. And here's just a little interesting look at how much energy we do generate from the start, but actually how much is used and lost during this process of conservation of energy. So really nice conversion at the top here of the types of energy, how much is lost, and how efficient actually our energy production systems are. Maybe you might come up with the most efficient energy power station the world has ever known and solve our issues of power consumption and loss. Who knows? So there we have it. Hopefully you now know how to define energy, the three major types and lots of examples of each, how they all are interlinked and change, and most importantly, the law of conservation of energy. Thanks for listening. Again, any questions, make sure you write them down and you come and see me in class. I'll catch you there.